Hi everybody. In this video, we're given a group G and then a new set which is called delta G, which looks like pairs, right? Pairs of elements, not the fruit. So the elements all look like G comma G. So there's just a repeated element where this G comes from the group G. We put an operation on this set given by, well, if you have two pairs of elements which have the same element in each component, G comma G, and then H comma H, you multiply them by simply multiplying the two elements together in each component. And the claim is that this delta G with this operation star is a group. Okay, fine. What do we need to do to prove this? So first thing, it's certainly a binary operation, right? So is this a binary op? Sure, right? This GH is still an element of delta G. Why? Well, G is closed under products, so we know that that's in G. And then we also see we get the exact same element in each component. Again, because G is a binary operation, so which means the product is a function. Okay, so we're good there. How about associativity? So I claim this associativity is going to follow from the associativity in G. So let's say I have some G, H, and K in my group, and that's going to give me three sets of elements in this delta G. So GG, HH, KK all in delta G. And now I multiply. So I have GG star HH. I'll do that first. And then I star that answer with KK. So when I multiply first in the brackets, I'm going to get GH. And then we'll star with the KK. And when I do that, I'll get GHK and GHK, where, note here, I'm leaving the parentheses because that's really what I'm doing. I'm taking the product GH and starring it with K, right, or multiplying with K. Now, here's where I get to use the associativity in G. The associativity in G says I can move these parentheses around. And we didn't move them, did we? We'll write G times HK and G times HK, where now the HK are associated. And now I can break this back up. I can write this as GG star with HK comma HK. And then I can break that HK up. So I have GG star, and now I have HH star KK. Okay, so this shows that I have associativity, right? This line and this line. Okay, next I need to have an identity element. All right, well, the identity in the group, if you called that E, so E equals the identity of G, well, seems very likely that E comma E would be the identity. So let's check. If I multiply on the left by EE, I'll get EG, and, well, sure enough, that's GG. And then remembering I have to check both directions. Okay, but it works similarly. So GE, which is GG. Okay, so I have an identity element. Finally, inverses. Well, if I have some G and G, then that's going to give me this G comma G. And what do I suspect the inverse is? Well, I know little g has an inverse in G, so I just put that in both components. And now I get G inverse, comma G inverse, which is equal to EE, which is my identity. Okay, and of course I do it on both sides, but no big surprises coming here. Except we don't need a comma there. All right, and that equals EE. All right, so we have verified that delta G is in fact a group. when you put this star operation on it. This delta G is sometimes called the diagonal subgroup of G cross G. So just for fun there, delta G is a subgroup of the Cartesian product. In the Cartesian product, that's where you're allowed to have any set of pairs here, right? So you can have a G from G, but also a different H from G. But this delta G will be a subgroup.